Yes, good morning to all. So today we are going to discuss about stereochemistry of 1,4 disubstituted cyclohexane. Last time we have seen the stereochemistry of 1,1, 1,2 and 1,3 dimethyl cyclohexane. So today we'll discuss about that is stereochemistry of 1,4 dimethyl cyclohexane. So just I have shared my screen. There's a four type of the dash substitution pattern. Type 4, 1, 4 die substituted cyclohexane. So here you are having a benzene. In this benzene, if you draw this benzene, on this carbon number 1, there is a hydrogen. And this hydrogen from carbon number 1 and carbon number 4, if it is replaced by here methyl group CS3 and CS3, so it is called as 1,4 dimethyl cyclohexane. So firstly again we have to draw their structure and then we learn its that is the stereochemistry. So again here we have to see its geometrical isomerism. Geometrical isomerism. In geometrical isomerism, we have to see cis and trans. So last time we have seen how to draw the cis 1,4 dimethyl cyclohexane. So for this one, we have to draw the structure of cyclohexane. So I told you first we will draw the structure. Here we start from this one, then we have to draw a line parallel to each other. The length of both two lines is same, and this line and this line, it is parallel. And this line and this line is parallel. So one structure. It undergo a ring flipping. When it undergo ring flipping, then it will convert into corresponding conformational isomerism. So it go down the plane, then it go above the plane. So here I start from here, it go above the plane, and here you have to write the other carbon here. We have discussed already how to draw the structures. So here I am not going to discuss that one. Then we have to draw its mirror images. So if you draw its mirror images of this two structure, then again here it go down the plane, then it go down the plane in this way. So we start from here, So it go down the plane, right? Then we start from the next one is here. It go like this one, and then this carbon is here. So just have to join this, and we will get such type of cyclohexane. Similarly, you have to draw its mirror images. So this is the, it will go down the plane, then it go above the plane. So in this way, we have to draw such type of cyclohexane, right? And it also undergo ring cleaving. Okay, then we have to give the numbering. Number 1, number 2, number 3, and number 4. Number 4. Now we have drawn the structures. Now we have to see 1, 4. So I will give the numbering first. So numbering here is a 1 and 2, 3, and your 4. Right? So these are 4. So firstly we'll draw the cis. Suppose if I write this bond, axial bond, is above the plane. It is above the plane. So this will go down upward direction. So it is axial. So they are the cis, means 1, 2, 3, 4. On the carbon number 4, it should be also above the plane. So here axial go down the plane. So equatorial go above the plane. So you have to draw equatorial. So it is axial. It is axial. So you have to draw equatorial. And here equatorial will be like this one. Equatorial. So axial and equatorial. So the methyl group. So first I will draw all the that is a, it's a mirror images. Mirror images will be the 1 and carbon number 4. It is this one. This axial becomes equatorial and equatorial becomes axial. So here is a axial. Number 4, here is a axial. Now it's mirror images. Here is axial and here is a also axial. And the remaining are the, that is, here is a axial and here is also axial, mirror images. And here is equatorial. Equatorial, here is also equatorial. Now here equatorial and here also equatorial. So you have drawn the axial and equatorial bond in which carbon number 1 and 4. So it is carbon number 1 and carbon number 4. It undergo ring flipping. So here is the carbon number 1 and carbon number 4. It undergo, here it's mirror images. So carbon number 1 and carbon number 4. So the two methyl group, they should be cis. So for cis we have to draw here. Suppose if I write here methyl, it is above the plane, right? It is above the plane. So this methyl should be also above the plane, means it is a axial equatorial. So in this case, the methyl group, either they are the axial or equatorial. Similarly, it undergo ring flipping, means equatorial and axial, right? So this axial equatorial. Similarly, we can draw here. Here is a axial. Here is a equatorial. Right. Similarly, it undergo ring flipping. So this axial becomes equatorial. So it is equatorial. And here, there is above the plane, means here it is axial. So either this methyl is axial or equatorial, axial equatorial or equatorial axial. Similarly, we can draw the methyl group here CS3, and here the axial CS3, and the remaining are the hydrogen. So I can draw the hydrogen here H. We can also draw the remaining hydrogen also, but I have written only the hydrogen and methyl. They are at 1,4 position. Now I will draw one more axial bonds. 1, 2, 3. Carbon number 3. Carbon number 3. 1, 2, 3. Carbon number 3. Right. 3. 1, 2, 3. So here also 1, 2, 1, 2, 3. Here 1, 2, 3 means this will go this one. Here axial 1, 2, 3 here. Right. And 1, 2, 3 this one. Here 1, 2, 3 this one. 1, 2, 3 here this one. Right. 1, 2, 3 this one. So just I have written the hydrogen at a 3 position. So again I will write the hydrogen here H, here also H, here is the H, right? Hydrogen, and hydrogen. When you can write the remaining hydrogen also. So we have to see the stereochemistry of this compound. Now here you will see that cis is possible when the methyl group is the axial or equatorial or axial. So it is a cis. Now next point you have to see, that is what is the position. Number one point, it's the position of cis 1,2 dimethyl cyclohexane. Cis 1,2 dimethyl cyclohexane. So the position is 1 and 4 positions. So not 1, 2, it is 1, 4. It is a 1, 4. 1, 4. Position is 1 and 4. Position is 1 and 4. So the position is 1 and 4. Number 2 point, we have to see it's a geometrical isomerism. Geometrical. So for cis, what is the geometrical isomerism? Either it is a axial equatorial or equatorial axial is the geometrical isomerism. Number 3 point, so it's optical isomerism. Optical isomerism. In optical isomerism, so here if you see this model, you'll find that this methyl and this methyl, they are at 1,4 position, and this 4 and this 4, it is at a 1,4 position. So here we'll observe that the methyl group at 1 and 4 position, 1 and this 1 position, they are the mirror images. This 4 position, they are also mirror images. So if you prepare a model of this one and if you put on one, then it say that they get superimposed, means they are not enantiomers of each other. They are not enantiomers of each other. So one and this three, even though they are the mirror images, but they superimpose. Why? Methyl methyl they get superimposed, and this methyl methyl also they get superimposed because they are at a 1,4 position. So they get superimposed, means they are not enantiomers. They are not enantiomer, right? So here they are not enantiomer. And if you pass a plane passing from carbon number 1 and carbon number 4, so it contains a plane of symmetry. It contains a plane of symmetry. So it contains plane of symmetry, means it is an optically inactive compound, right? So optical activity, as it contains plane of symmetry, it contains how plane of symmetry uh, from C1 to C4. So it is optically inactive compound. Optically inactive. So this compound is optically inactive compound, right? So you have seen the this cis 1,4 dimethyl cyclohexane is also optically inactive compound. Why? Because it contains a plane of symmetry. Now next point number 4 is stability. We can discuss stability in terms of its energy. In terms of its energy. So here, if you see this compound, the structure number 1, 2, 3, 4. We have added also. We have to also add one more. 1 and 3. These are the conformational isomers of each other, and 3 and 4. These are also conformational isomers of each other. So you can also write one more point: conformational isomers, right? So here, suppose if I write here 4, or you can write here number 3, conformational isomer, then it becomes 4 and becomes 5. Conformational isomer. Conformational isomer. So which are the conformational isomer? 1 and second, these are the conformational isomers of each other. Similarly, 3 and 4, these are the conformational isomers of each other. Why? Because they can interconvert into each other. So that point you have learned in every substitution pattern. Now here we have to see its stability. So in stability, if you see, if you take in structure 1, 2, 3, 4, you'll find that one of the methyl is axial and other is equatorial. When it is equatorial, of course, it is I from all type of interaction, means its energy is 0. But when the methyl group is in the axial position, then in that case, there is a 1, 2, 3, 1, 3 diaxial interaction. So there is the presence of 2, 1, 3 diaxial interaction. So for each 1, 3 diaxial interaction, you have to add 0.9. So this compound contains 2, 1, 3 methyl hydrogen, methyl hydrogen diaxial interaction. And for each you have to add 0.9. So 2 into 0.9 is equal to 1.8 kilocalorie per mole energy. So this is the energy of this compound. So you have seen cis axial equatorial or equatorial axial. So this is the energy of this compound. Now we have to see the next type, that is a trans 1,2 dimethyl cyclohexane. So similarly, in this way you have to trans 1,4 dimethyl cyclohexane. cyclohexane. So here in trans, you have to see again first point, that is the position. What is the position? Position should be 1 and 4. Number 2, geometrical isomerism. So here we'll make a change about the cis, then we'll see about the trans. Trans trans 1,4 dimethyl cyclohexane. So for trans, what you have to see, suppose if I put one of the methyl is axial, now other should go equatorial, above the plane. So other should go down the plane. So at one there is axial. So here this hydrogen on the carbon number 4 should be, that is a axial. It should be the axial. So just I have to change the group on the carbon number 4, right? And then we will discuss this trans. Now the methyl group at the carbon number 1 is axial. So this should be also axial, because carbon number 1 methyl go above the plane. So at carbon number 4 it go down the plane. Axial, and here is a hydrogen. It's a mirror images axial, and here is also axial. Now you know, when ring filming takes place, in that case the carbon number 1 here, it becomes equatorial. So this becomes equatorial. And the carbon number 4, it was axial, it becomes equatorial. So it becomes equatorial. So just you have to draw the equatorial. And carbon number 1 is equatorial. And here the carbon number 4, it should be also equatorial, CH3. And you have to remove this axial by the hydrogen, this axial and this axial. So just I will draw axial bond. Here is the H and here is also H, right? Now again let us see the trans 1,2 dimethyl cyclohexane. Methyl group is axial. At carbon number 1, it is going above the plane. So for trans, the group should be on the opposite side. So on the carbon number 4, it go down the plane. So they are on the opposite side. It's a mirror images number 3, axial, and here axial. Here is a H. It undergo ring flipping. So structure number 2, axial becomes equatorial. So it is equatorial, and also number 4 is also it's a mirror images, right? Now you have drawn the structure. Now you have to learn it's a stereochemistry. So in stereochemistry of this trans, first point is a position. So what is the position? Position is 1,4 dimethyl. Number 2, you have to see the geometrical. So in geometrical, we have seen that either it is a axial or equatorial, axial or equatorial, right? So both groups either axial or both groups may be equatorial. Then they are on the opposite side of the general plane. Number 3 point, conformational isomer. It is common for all because one can convert into a second. These are the conformational isomers of each other. Similarly, the structure number 3 can be converted into structure number 4. So we can write here the 3 and 4, right? The 3 and 4, these are also conformational isomers of each other. That was in number 3. Number 4 point, optical isomerism. Now here you have to again check whether it contains any elements of symmetry or not. So here you see that if you see any structure, structure number 1, 2, 3, 4, and if you pass a plane passing from carbon number 1, and carbon number 4. So here we can pass a plane passing from carbon number 1 and carbon number 4. So here we'll see that it will pass from carbon number 4 and carbon number 1. It will divide this into two equal half parts. It will divide into equal half parts because the methyl will divide into two parts. Similarly, this carbon and this carbon, they are on the opposite side, and the carbon number 4 again we can divide into two equal parts. So it contains plane of symmetry. It contains a plane of symmetry. Similarly, also we can write there is a presence of a center of symmetry. There is a presence of a center of symmetry. Suppose what is by center of symmetry? It is a center present in a molecule. Suppose if you write this center here, so if you write a line passing from this center to any group, for example methyl group, right? For any group, for example methyl group, right? So here, and again we extend in the opposite direction, then it will meet into the same group. So it is called as the center of symmetry, right? Center of symmetry. Similarly, suppose if I write this methyl, this hydrogen, so I can write a line passing from this center to this hydrogen, and again we can extend the that in the opposite direction, so it will meet into the same group. So it is called as a center of symmetry. It is called as a center of symmetry, right? So this contains a center of symmetry, right? So and if even though if it contains any one element of symmetry, then it is an optically inactive compound. So about the optical activity, it contains the plane of symmetry. Number 1, it contains plane of symmetry, plane of symmetry through that is C1, C4, just you have drawn. And second, it also contains a center of symmetry. Center of symmetry, right? So it contains plane of symmetry and a center of symmetry. That's why it is a optically inactive compound. So this compound is optically inactive, right? So it is optically inactive. Just same thing. It is optically inactive compound. So this compound is a optically inactive compound, right? Optically inactive compound. So this is also optically inactive because it contains any elements of symmetry here in this plane of symmetry and center of symmetry. Now last point is the stability, right? Number 5 is the stability. Stability, here we see that there are two types of the conformation. One is axial and other is equatorial. So firstly we will see what is energy of axial, right? And then we'll see the energy of equatorial and equatorial. As the groups are axial, in this case if the groups are axial, here if you see in this case the methyl group on the carbon number 1, so they undergo interaction with carbon number hydrogen on the carbon number 3. So there is a presence of 1 2 3 1 3 diaxial interaction. Similarly 1 2 3 1 3 diaxial interaction. So due to one methyl group you are having a that is a 2 1 3 dimethyl interaction. At the same time here the methyl group on the carbon number 4 It may also undergo interaction with 1, 2, 3. The hydrogen on the carbon number this 2, right? Similarly, 1, 2, 3, this one, they also undergo interaction with this one. So the hydrogen on this carbon and the hydrogen on this carbon, they undergo interaction. So there is a presence of 2,1,3 dimethyl interaction, diaxyl interaction due to the methyl on the carbon number 4. So total there is a presence of 4,1,3 dimethyl diaxyl interaction, right? So here we'll write for this axial 4,1,3 methyl hydrogen diaxial interaction, diaxial interaction, diaxial interaction, right? So the total energy will be 4 into 0.9 kilocalorie per mole energy. So is equal to, so 0.9. So 0.9 into 4 is equal to 3.6 kilocalorie per mole energy. So 3.6 kilocalorie per mole energy, right? So this is the energy of axial. Now equatorial. If you see the equatorial, in this case, you will see that the methyl group, they are maximum away from the structure. So there is no interaction. Methyl equatorial is also equatorial. So there, of course, there is the absence of 1,3 dimethyl diaxide interaction, and also as they are at 1 and 4 position, there is no butyl Gaussian interaction, skew interaction. That's why the energy of this one is found to be 0 kilocalorie. So here the energy of this one is equal to 0 kilocalorie per mole. It is found to be more stable, right? So this structure is found to be more stable. So this is structure number second. Now we'll arrange their energy. So we can arrange the energy of this one. So the energy of this we can arrange. If you see, the energy of cis is found to be 1.8. So in terms of stability of 1,4 dimethyl cyclohexane is found to be more stable when it is equatorial, right? When it is equatorial, it is found to be more stable. So here, if it is a 1,4 and cis or trans, so trans is found to be more stable. So trans 1,4 and equatorial is found to be more stable. Why? Because its energy is 0 kilocalorie. The next one is a 1.8, and 1.8 is either it is axial equatorial or equatorial axial. So here cis 1,4 either it is axial equatorial or equatorial axial, right? And less stable is found to be trans 1,4 axial, trans 1,4 axial and axial. You can also write energy. Trans is having energy 0 kilocalorie per mole. Then cis is having energy 1.8 kilocalorie per mole, and that of trans is found to be 3.6 kilocalorie per mole. kilocalorie per mole. So this is energy of this compound. So you have seen the energy of this one. So it's found to be more stable. Trans is found to be more stable. So in this way, we have seen the cis and trans 1,4-dimethyl cyclohexane. So here, in terms of optical activity, if you see, both are optically inactive. Right? Both are optically inactive. In this case, both are optically inactive. Right? So the number 4 point here, both are optically inactive, right? And we have seen about the energy. So in this one, what you have to learn? You have to learn the position, then geometrical isomerism, then you have to write down the cis and trans, when it is cis and when it is the trans. After that one, we can see the conformational isomerism. If you write the four structure, we can write same thing, one and second, third and fourth. These are the conformational isomers of each other. Why? Because they can interconvert into each other. They can interconvert into each other. Then about the optical isomerism, we have to check whether it contains any elements of symmetry or not. If it contains any one elements of symmetry, it is found to be optically inactive compound. And last point, that is about the stability. The stability we can explain in terms of, that is, energy. So more the energy, less is the stability. Less the energy, more is the stability, right? So here we have to check whether they are the axial or equatorial. If they are axial, then there is a presence of 1,3 diaxial interaction. So it is found to be somewhat more energetic and less stable. But if it is equatorial, there is no any interaction. We have to check whether it contains a butane skew interaction or not. And generally, the 1,2-dimethyl contains a butane skew interaction. Remaining all, they don't contain a butane skew or Gaussian interaction. And we can also arrange their energy like this one, right? So in this way, we have seen about the 1,4-dimethyl cyclohexane. It's a stereochemistry. If you have doubt, you may ask in stereochemistry of disubstituted cyclohexane. Stereochemistry of disubstituted cyclohexane. So on this disubstitution, they ask two questions to explain its stereochemistry. So if you know one, remaining all are same. Firstly, we should know how to draw the cyclohexane. If you know how to draw cyclohexane, then you'll find that we can write its position either 1, 1, 1, 2, 1, 3 or 1, 4. After writing position, we can write it's a geometrical isomerism, cis or trans. Cis, they are on the same side of the gender plane, and trans, they are on the opposite side of the gender plane. And after writing the cis and trans, then we can go for the conformational isomerism. What is the conformational isomerism? These are the stereoisomers which can interconvert into each other. So they are the conformational isomers. And this point is common for all: 1, 1, 1, 2, 1, 3, and 1, 4. And next point is about your optical isomerism. So here, if it contains any one elements of symmetry, we have seen the elements of symmetry. There is a plane of symmetry, center of symmetry, alternating axis of symmetry. So if it contains any one, then it is also optically inactive compound. We have seen the criteria for the optical activity. It contains asymmetric carbon atom, but it is a cyclohexane, so we cannot explain the asymmetric carbon atom. So we have to go for the, that is, whether it contains any elements of symmetry or not. So here, if it contains any one elements of symmetry, then it is optically inactive. But if don't contains any elements of symmetry, then it is optically active compound. And last point, we have to see about the stability. Stability we can explain in terms of energy. So here, if you remember the only cyclohexane, we have to write the four structure 1, 2, 3, 4, and then we have to write their axial and equatorial bonds and write down their position. then we can explain this point. So prepare this point, this topic today only, right? And try to make a practice how to write cyclohexane, how to write cyclohexane. So while writing cyclohexane, so here, just here, uh, you have to write this two line parallel, right? Here, this two line parallel, they are opposite to each other. If you want to write this carbon above the plane, so the length of the downward line should be more, and it go upward. Similarly, this one. So the opposite bonds, they are parallel and having the similar length. So if you make a practice, then you can write its structure. And if you know the structure, then remaining all points are very, very easy. So this topic is very, very easy and also very, very scoring. So only this 4 point you have to explain. Any doubt in this topic, you may ask. Yes. Any doubt? Ankita Verma. Any doubt? Fayaz. Shika Singh.
No, sir.
No. Okay. Thank you. Srikant. Yes. Shika. Yes. Any
No,
doubt?
sir. No, sir, no doubt.
No. Okay. Srushti. Srushti Vishwakarma. Supriya. Tushar. Vishal.
No, sir.
No doubt.
No, sir.
Okay. Yes. Any doubt, Vishal? Okay. So in this way,
No, sir.
okay. Thank you. In this way, we have completed this topic. Right? That is so. This chemistry topic is very, very easy. Only we should know some basic concept. One, you have to draw the cyclohexane. Number one. Number two, we should know axial bond and equatorial bond. We should know the general plane or the average plane. And after writing this one, you should know the ring flipping. Ring flipping, the conversion of one chair into the other chair is called as a ring flipping. And then draw the cyclohexane and learn the stereochemistry with number one position 1 1 1 2 1 3 1 4. Number two, geometrical cis or trans. If they are on the same side, cis of the general plane. If they are on the opposite side of the general plane, it is a trans. Then we have to go for the next, that is the optical conformational isomerism. Conformational isomerism, this point is common for all. 1 can convert into 2 and 3 can convert into 4. And you have to check 1 and this 3 whether they are the enantiomers or not. What are the enantiomers? Enantiomers are the non-superimposable mirror images of each other. You can also check diastereoisomers. What are the diastereoisomers? Diastereoisomers are the stereoisomers which are not mirror images of each other, which are not mirror images of each other. So in this case also we can write the diastereoisomer. Look here, here is the axial, right? In structure number 1, here is the axial, here number 4 is also axial. So structure number 1 and structure number 4, these are the diastereoisomers of each other. These are the diastereoisomers of each other. Why? Because they are stereoisomers, but they are not mirror images. Why? Because methyl is axial, and here is a equatorial and equatorial, means they are not mirror images. Means 1 and 4. Similarly, second and third, these are diastereoisomers of each other, right? So in this way you have to go for this one, right? And after that one you have to go for the stability. So you have to check the methyl group is axial or equatorial. If it is equatorial, it is away from all type of interaction. There is no interaction except if the two groups they are at 1 and 2 position. So there may be the presence of butane skew type of interaction. Methyl group they are at 60 degree, then you have to add 0.9, and for remaining one 1 3 and 1 4, so there is no such type of interaction. So here again you have to check whether they are at axial. If they are at axial, then there is the presence of when the methyl group they are at 1 and 3 position, at 3 position there is a hydrogen, so there may be presence of methyl hydrogen diaxial interaction. So you have to add 0.9. So in this way you have to write. So write down the structure, write down the group, and then discuss this point. And with this point only you have to write down 1 or 2 lines. So let them ask any question, you can write. So it is a very easy to understand, very easy to write also, right? So last point that we have seen the stability, right? So in this way we have seen this one for dimethyl cyclohexane. Try to write the questions in your textbook, in your question bank, in your university question. You can refer the book that is called as Organic Chemistry by Morrison Boyd, Stereochemistry by P.S. Kelsey, Stereochemistry by Elil, and also you can use a textbook that is a textbook of this Organic Chemistry Semester 1 by the Manali publication and also by the Nirali publication. You can also use Organic Chemistry by the Claydon. So these are some of the good books we have refer for this lecture, right? So I think if you don't have any doubt, then we should stop here, right? Uh, Thanks to all. Thank you, and you can leave the meeting. Thank you.
Thank you, sir.
Thank you,
Thank
sir.
you,